So let us continue our discussion with three-phase transformer connections, and I will quickly review what I told in our last class. That is, three-phase transformer connections will be generally represented by vector groups. And just to recollect that in a transformer nameplate, on the nameplate of a transformer, the connections will be written as either YY6 or DD6 or YD1, DY1 like that. This 6, 1, etc. actually describes the lead or lag angle of the secondary voltage with respect to the primary voltage. Now remember that the 6 corresponds to 180 degree phase displacement, 1 corresponds to 30 degree lag, depending upon the position of the hour hand with respect to the minute hand. And all these voltages, this angle, lead or lag, will be described with respect to neutral of the respective side. Even if the side is delta connected, we should consider the neutral, that is the artificial neutral with respect to that. So that we described in detail. Now after that, what I told that 3 single phase transformers can be connected as a 3-phase transformer, and you can transform a 3-phase voltage from one level to another nicely, no problem. But also a 3-phase transformer can be constructed as a whole. So we were starting that. So if you imagine that 3 single phase transformers are placed like this with a central common core, and each limb, outer limb, is having 2 sets of winding. One will be primary, another will be secondary, and the primary turns are equal, that is capital A1, A2, B1, B2, C1, C2 equal. Similarly, small letters correspond to secondary terminals. The number of turns are suppose equal. Then if you apply balanced 3-phase voltage to A, B, C, then 120 degree apart voltages will be applied across each of the winding, and the voltage induced in the secondaries also will be 120 degree apart, and you will get a balanced 3-phase voltage on the secondary side. But important thing which should be noted here is this: the flux produced by each one of them, instantaneous flux at any point of time meeting at this point, will vanish. Okay, therefore in the central core there will be no flux flowing. So the idea was, therefore you can remove this material in the central core. That is, you could have a structure like this now for a 3-phase transformer. That is this one, this side, suppose this side, this is like this, and then another side will be somewhat like this. Are you getting this way? And the third side will be like this. In the central portion there will be no iron, like this. I think it gives you the idea. So here the coils are wound. Here the coils are wound. So this iron you can straight away remove, because it will never carry any flux under any condition, load or unload like that. But still the structure is somewhat awkward. It will occupy larger space. Is not? There will be 3 wings. A transformer having, it will occupy larger floor space. Are you getting? So what simplification after this is done is important to note, that from this, suppose you now construct a 3-phase transformer in this way. Like this, a rectangular shape, and like this here. So here this side is there. Similarly this side. So what I want to tell, that you use stampings having two windows. These are iron. These portions are iron. And stampings are stacked together to give you the thickness or width of this one. And windings you place it here. On each of this, there will be 3 limbs now. On each of the limbs you place 2 sets of winding. One for primary, another for secondaries. Here also I am not drawing because of clarity. So each limb will correspond to a particular phase. Now what is the difference of this one with this? First thing, you get a greater advantage. It is now in a shape which will not occupy so much of flowed area like a Y. If you take from the top, if you want to see this structure, it will be like this. Is not? It will be like this. So the area covered to keep the transformer will become more. But now if you look from the top this side, it will look just flat, straight. Now what you sacrifice in order to get some simplification in the construction, that I want to point out. In this case, if a transformer, 3-phase transformer is constructed in this manner, then you note that when you energize, secondary suppose no load condition, each winding will produce its own flux, phi A, phi B, phi C, like this. It will be produced. Now the reluctance of the path through which each of the flux flows are equal in nature. But here it will not be like that. For example, this is A phase coil. Similarly, here you have B phase coil, only primary I am drawing. And here you have suppose C phase coil. You connect it in star or delta fashion properly and give 3-phase supply. Then also phi A will be produced here. Phi B will be produced. Phi C will be produced. The path traversed by each of these fluxes are different. Phi A, phi B it is same, phi C it is somewhat different. They will perhaps vanish here or there. Therefore, the magnetizing current necessary will become different for different phases. Are you getting? How do you calculate magnetizing current? You suppose know this much flux has been produced. You calculate B, is not? From B you calculate H. H is Ni by L. L is what? L is the length of the path through which this flux flows. For B phase it will be only this much. For A phase it will be this much, like this. So there may be unbalanced in the magnetizing current when the transformer is under no load condition. Okay? But that is sacrificed. Let that small current be little bit of unbalanced. How does it matter? But you get a great simplification in the construction of the transformer, and it will occupy lesser space, like that. So remember that the magnetizing current in the windings may be different. And as I have pointed out already, that given a transformer rating, magnetizing current is of the order of 2 to 5%, 2 to 3%, magnetizing current alone, not no load current. It will be about 2%, 3%. And they are different. At that level of current, there may be slight unbalanced in them. That we sacrifice. No load current we sacrifice. However, you will get a 3-phase transformer like this. Now, the important point I would like to come. So, I can have a 3-phase transformer by using 3 single-phase unit, that is bank of 3-phase transformer, like this. And I can have a 3-phase unit transformer as a whole. This, I think, is now clear to you why it is called a bank of 3-phase transformer and a single 3-phase transformer. Now, how a 3-phase transformers will be rating of three-phase transformer, how they are given. First I will tell that. Rating of three-phase transformer. What will be specified on the nameplate? In case of single-phase transformer, I know kVA, voltage ratio, frequency will be mentioned. Now, when a transformer is manufactured as a three-phase transformer, a typical rating on the nameplate you will find it like this. Say 10 MVA, suppose I say. (6600) volt stroke say 400 volt, 50 hertz, three phase. What else will be mentioned? The connection on the nameplate of this transformer. And perhaps it will be mentioned like this. Say delta, D, Y, say 1. Like this. For easier calculation, what I will do is this. Suppose 10 kVA I take. Just an example I am giving numerically. And I will try to tell you what is what. Or say 100 kVA, 1 MVA transformer. A distribution transformer. Now this 100 kVA is the total rating that you must understand. Total rating, total three-phase rating, total rating. This 6600 volt is always line to line voltage of HV. And 400 volt once again is the line to line voltage of LV. This is the standard way of specifying a three-phase transformer. Can you tell me, suppose I ask you, what is the turns ratio of the HV winding? What is the turns ratio of the HV winding and LV winding? How much you will tell? Suppose I want to know what is NHV by NLV. This is may not be equal to 6600 by 400. At least in this case it is not. There you don't make a mistake. Here it should be NHV by NLV. The voltage applied line to line voltage, that is this connection is just simple diagram, delta, this side star. So this voltage we are telling it is 6600 volt, 6600 volt, and this side it is 400 volt. So it will be 6600 divided by 400 by root 3. That you should be very careful about. So turns ratio may not be equal to the voltage ratio, line to line voltage ratio. Of course it will be provided the connection is delta delta or star star. In that case there will be no distinction. Now from these ratings what we can find out easily? Like single phase transformer, we can find out the rated current of the winding. Suppose this transformer is operating at rated condition, say 100 kVA. How much do you think will be the rated line current? That how to calculate? We will calculate in this way. From any side you calculate. This is 400 volt. 400 volt. So at full load balanced three phase condition, once again that thing will invoke root 3 VLL IL, no matter whether it is star or delta connected, is the total kVA rating of a balanced three phase system. So on the LV side, the rating will be this side if you calculate root 3 into 400 into IL. This will be equal to your 100 kVA, 100 into 10 to the power 3. So from this you can calculate what will be the current, root 3 into 400. So much ampere is the LV side line current, ILV line current. That is this current you will be getting. What will be the line current of the HV side? Once again same thing, 100 into 10 to the power 3, that is the rated current, divided by root 3 into 6600 volt. So much will be this current. Once again you should note that whatever current you will be getting only the line currents by using this formula. Winding currents will be how much? It may be equal to the line current or may not be. For example, for the LV side, winding current is same as that of the phase current, and here the winding current will be now root 3 times less. Those things you should keep in mind whenever you work with a three-phase transformer unit, single unit of three-phase transformer. Why it is highlighted? Because when you connect three single-phase transformers as a three-phase transformer, on the nameplate rating of each single-phase transformer, it will be written as a single-phase unit. So after you connect, you can work out what will become its total kVA rating and voltage rating, etc. that I described earlier. So in case of three-phase transformer, this is how the ratings will be specified. Now coming to the advantage of this transformer with respect to three single-phase units, I will put it in this fashion. Suppose you have got 10 kVA single-phase transformer. Single-phase transformer. 3 numbers. You can get 30 kV output from this for balance loading. So, to cater a load of 30 kVA, there are now two options before me. One is you can have 3 10 kVA transformer and supply that 30 kVA load. Or you can have a 30 kVA three-phase transformer. Are you getting? Suppose a certain locality, the load demand is 30 kVA and you want to supply it with a transformer for change of level of voltage, like say 6600 volt to 400 volt. Try to understand the problem. Suppose a locality is there where the load demand is 30 kVA and your input voltage is 6600 volt by 400 volt. Then this 30 kVA can be supplied at 400 level when the input voltage is 660, either by using 3 single phase transformers, each operating 10 kVA, or you can buy a single unit of 3-phase transformer of 30 kVA rating. Is not? Now, which one you will prefer? As it is, if there is no fund crunch, etc., then the cost of 30 kVA transformer, 30 kVA 3-phase transformer will be definitely lower than the sum of 3 single-phase transformers cost. Because at least we can see this much, there will be lot of iron saving. Is not? Central limb goes and it is now a structure like that. So another extension of window, that's all, with respect to a single phase transformer. So you remember that cost of 3 single phase unit, 3 number single phase unit will be more than the cost of a 3-phase transformer unit. Obviously, of course, the three-phase transformer unit as such, 30 kVA rating will be definitely costlier than 10 kVA transformer. That is okay, understood, because 30 kVA etc. is there. So either of these two options are there, either this way or that way. Now which one you will prefer? You tell your common sense, something you come up with. Three phase. Okay, three phase we can select. Initially I will put some money and connect it. But these three phase transformers as a distribution transformer where a particular locality is growing up may not be that attractive. Why, I will tell you now. Three phase transformer you purchase and start supplying this locality, 30 kVA locality with a three phase transformer. With the help of a three phase transformer you supply. Now if any problem occurs in this transformer, this three phase transformer, then the power will be off in this particular locality. Suppose a fault develops in that three phase transformer, the winding becomes open, things like that. Then the total load has to shut off. No power can be given to these consumers now. So what is done generally to maintain a distribution system nicely, whenever a transformer is there, there should be some spare available to you. Suppose this transformer develops a fault, then you must have a spare transformer. At least after 1 hour you can restore the power by disconnecting this faulty transformer and that spare one into service, bring that into service. Like that way it is done in a practical power system. Now the moment you go for a three phase transformer to do that, you must keep that in mind, and you have to buy also a spare transformer, not a single three phase transformer. A spare transformer you have to buy. And once this transformer develops fault, you take it out, put this fellow into service, and maintain the other transformer in the meantime, and that one becomes now spare for any eventual situation. So in effect you have to invest for two transformers if you really want to mean business with your customers. There is no other way out. So from that point of view, do you think, although the initial investment may be slightly higher with three single phase transformers, that will be a better choice? Because you connect three single phase transformers, you purchase each one of rating 10 kVA, you purchase only another as spare, because it is unlikely all the three will become faulty at the same time. Are you getting? But a three phase transformer, and once a single phase transformer becomes faulty, you switch off the power, only take out that single phase transformer out, other two are okay. But that you cannot do with a three phase transformer. Because of what? Three phase transformer is a single unit. Suppose A phase develops a fault. It is not fair to energize B, C phase, some way you supply power and also at the same time maintain that winding. You have to take out fully or put it in service fully. There is no other way. Therefore, from this point of view, it may appear that three phase transformer, single phase units to supply a distribution load like this for this particular applications, perhaps three single phase transformer unit will be a better choice. I will tell you another advantage of using three single phase transformers first from the connection point of view. Okay. So anyway, of course you have to do a trade-off. What exactly should be your. Now coming to this point, stating the problem in this way, I will go a step further. Suppose a particular area where 400 volt supply is to be given with the help of a distribution transformer, and that area is developing. Okay, right now not so much of consumers present, that area is developing. Okay, and you have projected the future load in say 5 years or 10 years 30 kVA. Some small figures I am taking, it may be slightly higher. The projected load of this particular area is 30 kVA. some few consumers are right now present, maybe totaling about say 15 kVA like that. Now, it is of course futile to connect or buy a 15 kVA transformer right now and start supplying this fellow, because within 2-3 years the kVA rating will go up further. So what you can do, you can either connect 3 single phase transformers, each operating 10 kVA, and be rest assured for, have a nice slip. That is 10 years nothing is going to happen. These units, whatever we have installed, will be able to supply this load. But if you go by the connection of the transformer slightly this way, if you make a trick, you can save the initial investment a bit. That I will tell you first, how this can be done. Go to your DD connection, delta-delta connection. DD connection. Suppose let us assume it is DD0, DD0 connection. Any delta-delta connection. Now, I will not go into detail of terminal marking. Essentially, I will assume you have correctly connected. Okay. Suppose the primary side is delta, secondary side is delta. Like this, it is connected. And you have given 3-phase supply. Suppose this is transformer 1 primary, it's secondary. So this is transformer 1, 1 dashed, primary, secondary. Transformer 2, 2, 2 dashed. Transformer number 3, 3 dashed. Delta-delta connected transformer. And each of single phase transformers we are using, 3 numbers. Suppose the rating of each transformer, secondary side rating is suppose V2 volts and winding rated current is I2. Okay. Single phase transformers, secondary side rating is V2 and I2, let us assume. That is, each winding rating is V2, each winding current is I2. Now, when all the 3 transformers are present, how much kVA you can deliver? Rated current is I2, you can allow root 3 I2 to flow. So, total kVA that can be handled by this is root 3 into V into the line current, root 3 IL, that is 3 V I2 I2. 3 V2 into I2. That is the total kVA rating you can supply. This is understood. That is, each one is 10 kVA, 20 kVA I can supply, 30 kVA I can supply. Now, you just imagine, no fault etc. has occurred. What I have done, the second transformer, let us remove from the circuit. Suppose in the above connection, second transformer is removed. Then how the circuit will look like? It will look like this one. There I have simply removed that second transformer from the circuit, and still I have given 3-phase supply here. You give 3-phase balance supply to these 3 points. So transformer 1 is present, 1 dashed is present, 2 is present, 3 is present, 3 dashed is present. Now, what is the voltage impressed? Sinusoidal voltage. So, induced voltage here will be also sinusoidal. So, this voltage triangle, from the input voltage triangle, input voltage is balanced. Input voltage is balanced. Therefore, this voltage has got 120 degree difference. So the induced voltage here will be in phase with 1 and here induced voltage will be in phase in 3. Tell me whether you will get a balanced three-phase output voltage on the secondary side? Yes, you will get, because the input voltage is balanced. Okay. Although it is not there, if you connect a voltmeter between these 2 points, this voltage will be this one, resultant of these two. So whether you connect a transformer in position 2 or not, 2 dashed, if you remove it, then if you apply three-phase balanced voltage here, you get three-phase balanced voltage on the secondary side. And there will be step up or step down depending upon the number of turns. That means it appears that by using also 2 single-phase transformers, three-phase voltage can be transformed from one level to the other. So far we are telling to transform a voltage from one level to another in three-phase system, it may appear that we require always 3 single-phase transformers or a single three-phase unit of transformer we can do like that, fine. But a slight trick like this also shows that a balanced three-phase voltage can be transformed to another level by using only by 2 single-phase transformers. And this connection is called V connection, very popular, used V connection. It looks like a V, not delta, delta, start delta, the conventional connection. It is V connection. Now let us try to estimate what will be the kVA output of this particular VV connection. Suppose you connect a balanced three-phase load here. Tell me what line current you will allow to flow on this side. Rating is known, V2, I2. I2 only, because this current is same as the winding current. Your hands are tired. You cannot go now root 3 I2 like the previous one. And if I2 flows, I1 will be there, so I1 will come like that. It will come. This voltage is V2. This voltage is V1. So, how much will be the kVA handled by this open delta connected transformers? This is called open delta or V connection. In open delta, sometimes it is called open delta connection, open delta connection, or V connection, or V connected transformer, V connection I think, V connection. The kVA rating, total kVA that it can handle, total kVA handled, will be root 3 times the line to line voltage, that is V2, into line current, I2. So this is only root 3 V2 I2, not 3 V2 I2. Of course it should not be, because I am using 2 transformers. But it may appear, since I am using 2 transformers, so kVA, I would have been happy if it would have been 2 V2 I2. It is less than that. Root 3 is 1.73. Is it not? So this is the kVA, the individual transformer kVA, it is V2 I2. And both of them are fully loaded, but maximum kVA I can transfer to the load is only root 3 V2 I2. So with respect to your total three-phase system, if you compare, suppose 3 transformers were there. If 3 transformers were in use, kVA handled would have been 3 V2 I2. So it will be reduced by a factor of 1 by root 3. That is about 58% of this one, the kVA handled by a open delta transformer. So I can calculate the kVA. But the point I want to make is now this one. Suppose a instead of, first I will tell this point, instead of purchasing a single three-phase transformer, three number of single-phase transformers have been put, and it is supplying load. And suppose full capacity, developing business you forget, 30 kVA, each is 10 kVA, I am supplying 30 kVA. As I told you, one transformer may develop a fault, then you have a spare, of course. But what I am trying to tell, even if one transformer develops a fault, simply by removing that, you can supply some of the kVA, not the whole kVA now you can supply to that area. But with those two good transformers connected in the lines, I can maintain not 100% supply which I was doing earlier, that is 3 V2 I2. But now I will be at least able to do root 3 V2 I2. Some portions will be load shedding or things like that. That is, without investing any further, I can at least maintain that much kVA at that point. I mean, like that one should think. And second point I want to make regarding this problem, in a somewhat say undeveloped area which is now coming up slowly, where you project your future loads in say 5 years will become 30 kVA. But right now the load is less, but three-phase voltage is present, I have to give three-phase voltage here. Then instead of purchasing all three single-phase transformers, you purchase two now, 10 kVA, 10 kVA. Third one you will purchase later. With 10 kVA, 10 kVA, how much you can supply? Not 20 kVA, that is correct. But some percentage of that I will be able to. And that may fall within the small load now which is existing in that particular area. And in fact, this is done once the area is developed, then you connect, purchase another and go for this. So anyway, this you will gradually come to know if you read more of handbooks and things like that. This I will not tell much more right now. But the essence of the thing I want to communicate to you. So this is open delta connection is very much in use. Now another connection I would like to tell, this you read in books, this open delta connection and V connection. Now today I would like to tell you another connection which, why it is used, first I will not tell. But first I will tell you another connection, how this can be done also. Zigzag connection it is called. Zigzag connection. Zigzag connection it is called. Why it is called zigzag will be apparent after I do that. Now for this, what you will require in a three-phase transformer, that for a primary, suppose A1, A2, connection of three-phase transformer. For a single primary, there should be two identical secondaries available to you in order that you can do this connection. That is the first condition. That is, for example, A phase, on each limb of the three-phase transformer, there will be actually three windings. Suppose each leg of the three-phase transformers, there will be A1, A2, and two identical secondary windings, which I will be marking as A1, A2 and A3, A4. A3, A4. A1, A2 and another here. Separate windings. A3, A4. That is, on the construction, each limb or leg of the transformer, there will be now three windings. One marked with capital names, that is the primary winding, and there will be two identical secondary windings for each phase. And you can have another B1, B2, and here is, it will have also two identical secondaries, B3, B4. And then you can have a C phase, C1, C2, small c1, c2, small c3, c4. And remember that once again with this convention we have drawn, that is, these polarities are such that these first terminals are all dot, connected dot. Now suppose you join these three in star, primary star connected. Okay. So primary phasor diagram will be how? And you have given A, B, C supply to the primary. This is A1, this is B1, and this is C1. And this point is the neutral point, that is this N, which is A2, B2, C2. A2, B2, C2. Now, once this is energized, don't do anything to the secondaries. Let them be open circuited. Tell me now, what are the voltages available on the secondary side? You have now 6 voltages available. What are they? I will just draw here. This is A1, A1, A2, and another equal length A3, A4. A1, A3. These 2 voltages are available, same phase. And you have another here, B1, B2, and B3, B4. And finally, you have parallel to C phase 2 voltages available, C1, C2, and C3, C4. These voltages are just available the moment you energize, because A phase voltage is this. It is on the same limb. So these voltages will be in same time phase. Getting? That is, if you short simply A2, B2, C2, you will get that YY0 connection. Suppose you forget about others. Now, zigzag connection basically means when it is completed, it will be a star connection. Okay? Zigzag connection, you write down, is nothing but ultimately it is a star connection. Zigzag connection. Is ultimately a star connection. And this connection will be represented as, suppose primary star, secondary zigzag, and suppose 1 I want to do. 1 I want to do. So how shall I go? This is the primary voltage. Here I will once again draw. This is the primary. This you just listen carefully. What I am telling. A1, B1, C1. Now on the secondary side it is one connection. Therefore A phase voltage where it should be, I will first draw a line parallel to this that I have drawn. And secondary voltage will be lagging it by 30 degree. Is not? It will be lagging it by 30 degree. That is, after this star connection is over, if this is the neutral of that star connection, your secondary voltages should be like this. See, secondary will be ultimately a star connection. There will be some neutral. So, if it is one connection with respect to A phase voltage, that A phase voltage with respect to the secondary neutral should be 30 degree lagging. It will be here. Is that clear? Now, what I am trying to tell, you have these voltages available to you. these voltages available to you. A1, 6 voltages are available to you. And this point should be some A, it should come from A. Today I don't have much time, but I will tell this much, that this phasor, you just see, can be thought of as the sum of this phasor and this phasor. And this one you take, suppose A2, A1, suppose you take. And this one, it can be easily shown, this is also 30 degree, parallel to C phase. So take this one from some C winding. Either C2, C1 or C4, C3. Okay, suppose I take C4, C3. Similarly, this phasor, here something from B should come, A phase, B phase, C phase. And this can be thought of as sum of this plus this here. Here you write B1, B2. This one, where from it will come? A1, A2 I have already used. So it will come A3, A4. And lastly, this one can be thought of as this way. And this will be, it can be shown B3, what? B4. And this will be C1, C2. So after getting this, I will join it like this. A1 is A1. So A2 should be joined with, say, C4. A2 with C4. A4 with B2. And C2 with B4. C2, where is B4? Oh. Like this I will join. This will be, and A3, B3, C3 should be shortened. Now, why so much complicated star connection we do, that I will discuss in my next class. But one can have this way also, one connection which is used sometimes. It's called zigzag connection, for which you require two identical secondary windings for each phase. And you can try just as a rather like a quiz without this logically, what are the connection possible? DZ0, DZ6, you can see it is possible. Or YZ11 you can try. So today I conclude here, and day after tomorrow that test. Auto transformer and single phase transformers. For mid-sem, whatever I have taught today. When is your machine exam? Next week, eh?